Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 28, 2025, about 4 days ago. The headline result is bold: a forkless blockchain database that delivers about 100 times less storage and about 10 times higher throughput compared to a geth-based Fantom client. The paper is titled Efficient Forkless Blockchain Databases, and as we will see, the design choices make those gains feel quite practical. In short, it splits responsibilities into LiveDB for the current state and ArchiveDB for history, sidestepping Merkle-Patricia-Try overheads that waste I/O and space. On X, posts claimed the study could force chains to redesign databases, calling it a fundamental reimagining that puts Sonic Labs at the forefront, with moderate engagement around 200 likes. Alright, the previous segment highlighted why legacy tries inflate storage. Figure 1 illustrates that with a simple update in a Merkle-Patricia try. The left panel shows state x1, where keys map to values through shared paths. The right panel shows state x2 after changing value v4, which forces new nodes to be copied along the B to F path, so redundant structure persists and must be pruned later. This duplication explains why forkless chains suffer unnecessary I/O and space overhead. So, the previous figure showed how a single update bloated a Merkle-Patricia try. Figure 2 contrasts 3 architectures that respond to that problem. The left panel keeps one unspecialized StateDB that must serve both the virtual machine and historical RPC, which forces multi-version state. The middle panel shifts validators to a LiveDB only, so the virtual machine updates one latest world state. The right panel adds ArchiveDB beside LiveDB, which logs changes for historical queries while keeping validator processing fast. Alright. The previous figure contrasted architectures for validators and history. Figure 3 explains how LiveDB computes the state hash lazily. Attributes like balance, nonce, code, and storage each form their own hash trees, so only dirty leaves trigger recomputation. The A indexer maps addresses to record numbers, while the AK indexer maps address plus key to storage records, which enables constant time lookups. All attribute hashes and indexer hashes then combine into one state hash, which keeps updates fast and I/O low. So the previous figure showed throughput staying steady with the archive enabled. Table 1 reports storage at 50 million blocks, which directly quantifies the savings. The validator view drops from 1,600 gigabytes for pruned Merkle-Patricia try to 30 gigabytes for LiveDB, which is about 98% less space. For history, the archive falls from 17 terabytes with Merkle-Patricia try to 550 gigabytes for the SQL variant and 140 gigabytes for the key value design. These numbers make smaller, cheaper nodes feasible. So the previous figure reported storage gains. Figure 6 shows transaction throughput over a 50 million block replay, comparing the Merkle-Patricia try baseline to the new binary file design. The blue series sits around 5,000 transactions per second with fluctuations, while the red series hovers below 500 transactions per second. Both lines dip slightly past 40 million blocks because cache hit rates fall and input or output grows, yet the gap remains large. The result signals a consistent 10 times speed up for validation workloads. Wrapping up, 2 takeaways stand out: splitting duties into LiveDB for the latest world state and ArchiveDB for history eliminates multi-version overhead, and the dense, lazily hashed layout delivers about 100 times less storage with roughly 10 times higher throughput. The broader implication is cheaper, faster validator nodes, and more accessible full history. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.